Welcome back, physicists. In this video, unfortunately, first hour, I recorded the whole lecture and it had a hiccup at the end and it didn't save it and it just closed the program, so that sucks. But we are coming back in, and in this video, it's going to be a little bit shorter for you guys if you're watching this on the road, which is convenient, or if you just happen to be absent. Today, we are going to finish up 5.3, and we were looking at this last section as well, but I just want to make sure we're all caught up. Forces in two dimensions. Okay, now I believe the last thing that we were looking at was finding theta for a particular problem, but we're going to make the jump here real quick, and this is going to be a lot nicer for you guys, so you're actually getting the advantage here. But I'm going to start in, we're going to make the jump to dealing with inclined planes. So inclined planes and force. Now, when we're dealing with inclined planes, we're going to do something that's kind of strange, but we're going to make sense of it. Anytime that we're dealing with this, to set this up, free body diagrams are going to be so much more important. So for the setup, we're going to make sure that we can draw these pictures the same way, and it's going to hopefully make it a little bit easier in the end, despite it being a little bit strange sometimes. So right off the bat, whenever you're dealing with an inclined plane, the first thing that you're going to do when you're starting to sketch, and I'll just say this here, is we're going to sketch our free body diagram. That's always the first step. Now, what's unique about this is because we don't work on a horizontal surface anymore, our free body diagrams are going to shift a little bit, and it's going to be advantageous and helpful for us to do so. What's going to happen as we do these is we will make the incline, whatever it is, whatever degree it is, make that incline, the surface that whatever we're dealing with, sliding down or being pushed up, it doesn't matter. We want to make the incline the x-axis. Okay. In doing so, this does us a couple of things. The first thing that this is going to make happen right off the bat is it means that the normal force, Fn, which is perpendicular to the incline, is just going to be on the y-axis. Okay, that's the first big part. The second piece, theta, the angle of our incline, will be between the y-axis and the force of gravity, which I'm going to put in parentheses here. Remember, this is just going to be straight down. And straight down, meaning like directly vertically down on your page, not perpendicular to the incline. Okay, once we get here, we're going to then, once we have this sketched, we are going to have to work through, and I'm just going to put this really generally, do some trig. Okay. So, in working these, in class today, we looked at one example, and it's kind of clunky as we work through it, but it's not going to be clunky here. There's no questions, or at least I know the questions that people had before. If you want to work along with this, and you don't want to have to write this whole example down, I'm going to go to First Hour Physics on the Google Classroom, and past here, you will see that underneath all the assignments, we have this as, hey, attached, you'll find digital copies of any and all the documents. At the bottom, we have the Physics 5.3 examples. In class, we worked one full one together, and we did it a couple different ways. If you want to access that, go ahead and do so. I want to keep this visible for a moment at least, and we're going to do this example. So I won't be able to keep that completely visible. Excuse me. Excuse me. Maybe I will. We'll see. I'm going to resize this, do a little editing magic. Go ahead, open up that document, and when you resume, I'll have it resized in the appropriate size so that I can write it all here next to this. Okay, so here is number 3 from that PDF that's in the Google Classroom for you, and this is one that we worked in class. For this, I'm just going to talk through the process of how we draw these free body diagrams, and then I'm going to present you a couple different ways that one can handle this. And I don't care which way you wind up going with it, but let's just jump in. So we have this guy, Fernando, and he has a mass of 43 kilograms, so kind of small. He's sliding down the banister, which is just the railway on stairs, so he's taking a risk here, but he's sliding down the banister. We know that the banister makes an angle of 35 degrees with the floor or the horizontal, however you want to think about it, and we're trying to find the normal force between Fernando and the banister. So it's super weird to do, but I'm going to draw my x-axis inclined. And it seems strange, but check it out. I'm going to make it pretty much always go down this way. Now, this is my x-axis. So I'm going to make sure that I just go ahead and say, check it out. Here's x. And then I'm going to draw my y-axis as well. And we're going to put the y-axis perpendicular. And it always looks weird on my computer, but I think that this is a right angle. Okay, here it is. Now, as we deal with this, I'm just going to use this, and I'm going to draw my free body diagram on here. I'm going to let Fernando be right at the origin. Cool. There's Fernando. Now, as we start putting forces on this, we need to think about how they're going to act, and we're going to see this idea happen. I know that the force of gravity pulls straight downward, and I don't have a good magnitude for it yet, but I'm going to put it right here. Here's the force of gravity in purple. Okay. Furthermore, the normal force, remember, is always perpendicular to the surface, and I made that comment here. The normal force, though, is going to come right along this y-axis. I'm going to make it a little bit bold so we can look here. This is the normal force that we're after. Okay. There it is. Now, when we look at this problem, there's two different ways to approach it. Your book uses one angle, and I typically use a slightly different angle, but we'll make sense of that. When we move to these inclined surfaces, the normal force is no longer exactly equal and opposite to gravity, because all these angles change stuff. Gravity pulls at a different angle than the normal force pushes. So we need to make some adjustments. And one way to do this, if we have an angle theta, is I'm going to take just this part out, and I guess I don't even have to take it out. This gravity here, and let me get rid of those dashes. This gravity pulls downward, but I know that with respect to the way that this thing's going to move down this ramp, there is going to be a component of it that pushes down the ramp parallel to the x-axis, a component of gravity that does that, and there's going to be a component of gravity that pushes perpendicular to the ramp, which is going to be our normal force. So what I want to do, and there's two options that we can run with, I want to be able to make this force of gravity that we have the hypotenuse of a right triangle. Now, your book takes this approach. They'll go from here at the end of gravity and work horizontally until we get a right angle here. Okay. I'm going to move this force of gravity because I don't like where it's at. So let me do that really quickly. We'll move that force of gravity. Hate that. So we'll do it this way instead. We'll move this force of gravity. And I'm just going to write it in a slightly different spot. So here's my force of gravity instead. And it's still that same vector, I just moved the label. Now, this green part that I drew on the bottom, this is going to be the force of gravity in the x direction. And I can think about this gravity just pulls it down and to the right along the ramp. It's prettier without the arrows, but that green line right there is the force of gravity in the x direction. So Fg comma x. Alternatively, or more than that, we also have a component of gravity that pushes directly against my incline. So this blue segment, and this is going to be the force of gravity in the y direction. Okay. From our picture, we get this. Nothing too crazy, but a couple observations that I want to note. Right off the bat, in this problem, we're looking for the normal force. And it turns out that the normal force is perpendicular to the surface. We know that's true, but it's going to be equal to some of the gravity. Not all of it, because they pull at different angles. But right off the bat, based on this picture, what I see is that my normal force, Fn, is exactly equal but opposite to Fg in the direction of y. And by drawing this, I hope at least, that you guys can see that this is true. My normal force goes directly up along the y-axis. My gravity in the y direction goes directly down along the y-axis. Okay, this next part you do not need to draw, but I'm going to take a look at only the bottom right, so quadrant 4 of this. And I'm just going to resketch it underneath, and I'll assign colors as well. I don't need colors, I lied. That's going to be more work than it's worth. So there's FGY, FG in the y direction. Here is my x-axis, and here is f of g in the just vertical straight down. Okay, when I connect all these pieces, and I'm not going to make that an arrow. When I connect all these pieces, notice what happens. This triangle is exactly that triangle similarity stuff that we were talking about. I know that my incline for my ramp in this problem is 35 degrees. I'm just going to call this theta right here. Now, this picture, these two pictures are almost the same. I can get this picture. I'm going to undo it because I'd rather work on a separate one. But this is just this triangle. This triangle right here, I have put down here. Okay, in doing this, if you dig back through the stuff that we did, I know that this angle is also theta. That is this angle right here that we will call theta. And I have to write really small. There's my angle theta. Okay. If we want to just solve this problem using this angle, there's one thing that I hate about it, but we're going to look at it. I'm only looking at this triangle right here. So this is all that work that we did with similarity is so that I don't have to just magically tell you that this angle right here is theta as well. We did this similarity to see that these angles are going to have to match via angle-angle similarity and these right triangles. Now, with this theta now identified, we can boil this down into a much simpler problem. And each step along the way, there's some stuff that happens that I don't want to just be magic, which is why I'm going into the mathy explanations of stuff. But if I look at just the triangle that we have, this is it. This triangle is right here, where I know that this length is the force of gravity. That's a right angle. This distance right here is the force of gravity in the x direction, which it feels weird because it's at a diagonal, but it's the x direction parallel to our surface. And this right here is the force of gravity in the y direction, with this lovely theta right here. Okay, so I've taken this triangle and the fact that I know the normal force is just equal and opposite to gravity in the y direction, we can solve this. There's only one little issue that I have with it, but let's dig into that. From this angle theta on this pulled out triangle, I know that I can find the force of gravity and stuff, and I should have listed my knowns right off the bat, but let's look at it. Fernando has a mass of 43 kilograms. I know that gravity will pull down at 9.8 newtons per kilogram. And then finally, the only angle theta, or the incline of our ramp theta, is going to be 35 degrees. Sorry about the sniffles, I am not well. Okay, we are trying to find in this problem the normal force. All right. So hopefully you're pausing along the way. I'm going to get rid of a lot of this x-axis because I don't need that much space. And I'll switch back here, and we'll knock it out. Here is the x-axis. Okay. I am dealing with just this triangle, because if I can find FGY, I'll just change the sign of it to be positive, and I'll get my normal force. So let's dig into that, how we find this piece. From this triangle, I know that I can work out the force of gravity, because this is just mg. So I have that. We'll say this is mg, and I don't really have a color for that. I was using purple above, I suppose. Force of gravity equals m times g. If we look at this triangle, I'm looking for the adjacent side from angle theta, which is FGY. And I know that we can at least get the value of the hypotenuse. So, katoa, I'm looking for which one deals with adjacent and hypotenuse, and I recognize that it's ka for cosine. When we start plugging in, chugging through this then, I know that the cosine and I'm going to switch to black here. I know that the cosine of theta, or 35 degrees in this case, is equal to the adjacent side, which is our FGY, FG with respect to y, over the hypotenuse, which we knew was the force of gravity. And we can write it here as FG, or if you'd rather, and I know I would, I'm just going to use mg. Okay. To solve this for the force of gravity in the y direction, if I multiply both sides by mg, and I'm going to switch the sides that these are on, I would have the force of gravity in the y direction is just equal to, and I'd multiply both sides by mass times gravity, or the force of gravity, times a cosine of 35 degrees in this case. Okay, just using the picture, this isn't wild. There's nothing crazy that happens. I can see that this aligns, and I'm good with that. Where my only issue with these problems lie, and it's not really an issue, it's just something that I want to make sure we address. All the trick stuff that we've done the last few days, we've stressed over and over that x is typically represented by cosine and y is typically represented by sine. Cosine and sine are the points on a unit circle. If you just blindly follow formula, this doesn't quite work. And maybe there's an easier way to make this work, and we'll talk about that. But notice I have y, this vertical, being determined by the cosine. That is all right. It's strange that it happens, but it does, and it can, and it's all right. So if we just plug in what we have, let's just see how this shakes out. I'm not going to switch colors anymore. I know that the mass of this object is, or this person rather, is 43 kilograms times gravity, which is 9.8 newtons per kilogram, times a cosine of 35 degrees. When we type this into the calculator, and I'm going to grab mine real quick, and I'm going to make sure I'm in degrees, and I do 43 times 9.8 times the cosine of 35, we get 345, about 345 newtons. Okay, boom, check it out. The banister produces a normal force, F sub n, approximately equal to 345 newtons on Fernando. Okay, done. We have it, piece of cake. As long as you recognize that your picture is what's going to dictate it, you can do these problems without getting too crazy with things. If you do not like it, there's a couple alternatives. Typically what I do on this problem, and I'm not going to rework the whole problem. We did in class, but I don't know if it had a whole lot of benefit. I want you to make sure you have this jotted down. I'm going to work this problem again with just a slight difference. So if you need to pause it, do so now, because I'm going to erase like all this in 3, 2, 1. And I guess I'll show it because I'm going to erase it and then I'm going to redraw it real quick and we're just going to look. I'm going to use all the same knowns mostly. I don't need all that. Okay, so check it out. When I do these problems, I do not love the fact that that theta is the angle that we wind up using because bow ties and butterflies are always nicer. Looking at this, couple easy ways that we can change this to fit the trig stuff that we did. So I'm going to draw the same thing. Here it is, the x and y, and I'll make sure we mark them. We have x and we have y, and we still get that force of gravity pulling straight down. And I'll use my forces, I'll make them a little bit more bold. Here's gravity. Okay, what I would rather do, instead of using this angle theta that we've identified via that last one is right here, I would rather think of this angle that I'll call phi. Okay, if we deal with phi instead, we can work with a nicer triangle that fits in with that bow ties and butterflies idea. Instead of going this way to make our right triangle, I can just go straight up so it's in our bow ties and butterflies land. In doing this, we're going to get the exact same answer, but what will change, and what's super helpful to change in my mind, is that this red line now becomes the y component. So this is FGY. I'll label that FG in the Y direction. It's parallel to the Y-axis, and as long as I get its length, I will know the normal force here. It's not as easy to see in the picture, but it's the same number. And then if we had to, FG in the X direction is right on the X-axis. So FG to the X direction. The only difference here is the math is going to be a little bit more natural to follow through, and we can work this out. So what I mean by natural, and this is totally subjective, maybe it's not natural for you, and if it's not, that's okay. But if we wanted to find the force of gravity in the Y direction, which when we set it up the first time, we realized that, hey, that's the same as a normal force, we now get to use the rules that we normally would. If I look at phi, for example, and I'm trying to find the force of gravity in the Y direction, this is the opposite side, and this is the hypotenuse. So it still works out the same. I know that sine of phi, instead of cosine, which we used the first one, I typically associate sines with y. Sine of phi on this triangle is going to be the opposite length, which is the force of gravity in the Y direction, over the hypotenuse, which is this purple line, which we've already decided was the force of gravity just overall. Cool. Once we have this, we're good to just start cooking. I can solve this by multiplying both sides by FG, which means we would get force of gravity times the sine of, and I'm going to do a little thinking here, and I'm going to actually put in this value. Sine of, well, if this was 35 degrees at theta, then phi must be its complement and add up to 90, so I know that sine of 55 degrees is going to be phi. This angle right here has to be 55 degrees. Cool. Well, that's still just equal to, after multiplying both sides, the force of gravity in the Y direction. All of a sudden, these things start to make a little bit more sense. When we plug in force of gravity, when we did the original problem, I think it was a negative, or it wasn't negative because we just used G as 9.8. But if you type this in, you are once again going to get approximately that 425. The exact same thing happens. We get the same answer. So if we type this in, this is mg, that's the force of gravity, where g is going to be negative, and we'll make sure we do it this time, times the sine of 55 degrees equals the force of gravity in the y direction. So I've just substituted mass times gravity, and then plugging in, we get the same calculation. We get 43 kilograms times a negative is what I should have done that first time, 9.8 newtons per kilogram, times the sine of 55. Because I'm using this angle with my bow ties and butterflies. Cool. This winds up to be the same number. If you want to go back to your notes, I made a couple comments that are, I think, nice, but I don't want them to confuse you. Some notes to make with the trig here, just worth noting, redundant. But first one, if you give me an angle theta, so theta, just kidding, that's a phi. If we take theta and phi, which is that one, and we know that they're complements, which just simply means that they add up to 90 degrees, which is what happens when we deal with these quadrants. Theta and phi, yep, they make 90 degrees. If this is true, then we get a pretty handy relationship. The sine of theta is exactly equal to the cosine of its complement, or phi. And if we wanted to split this, it means that I could also take the sine of phi, and I know that that is exactly equal to the cosine of theta. Awesome. As long as we pay attention to where we're working at with a good diagram, and should have included negative on the first one, we're going to get these numbers using sine and cosine as we normally would. Because this relationship right here, it doesn't matter whether I use theta or phi, so long as the triangle that we draw is perpendicular to the x or the y-axis when we add that other piece. Cool. Last little piece, and as a more trig comment here, if we think about a triangle on the unit circle, I know that a triangle on the unit circle, that was right. Every triangle that we draw has an x and a y point on the circle that corresponds to whatever angle we're going at. And you don't have to draw the whole circle. I'm just going to draw the first quadrant so we can think about this. Remember that if here's my circle, no matter how big it is, and if it's a unit circle, I guess it's 1. For any angle here, and I'll call it theta, I know that this ordered pair can be represented as an xy, or if we're thinking in trig stuff, this x direction is just the cosine of theta. That's that length. And this y direction winds up being the sine of theta. From this, if we ever had to calculate out the tangent of theta, and we think about SOHCAHTOA again, tangent of theta we know is opposite from this angle over adjacent. And in this case, the opposite length is sine theta, and the adjacent length winds up being cosine theta. We now have a nice definition for tangent if we ever need to find it. All right. So this was the main discussion in class, this one problem done both ways. This weekend, I gave everybody an assignment, and it was just to finish one problem. I'm going to jump over here, and I'm going to copy and paste, and I want to look at this because oftentimes the hardest thing in any physics problem is just going to be like setting it up and starting. And there's some advice that I would like to offer. If you have questions on anything that we've done so far, I should have worded this earlier. Please make sure that you jot it down in your notes so you don't forget it. Okay. Your homework over the weekend is to finish number 4 from that worksheet, and then we'll look at 1 and 2 together. But on this problem, I want you to go ahead and I'll read it. We have a suitcase on an inclined plane, and I want to know at what angle relative to the vertical will the component of the suitcase's weight parallel to the plane be equal to half the perpendicular component. This is wordy, and it happens in physics because we need to make sure that we're really clear with how things are set up, but it does lead to maybe a little bit of intimidation at the start. I want you to pause this now and try to sketch the free body diagram with it. We don't have any knowns and things like that, other than I know what direction gravity goes. So pause it now and try that. I'm going to start talking about this and shove you in the right direction in just a moment. You should try it. Be okay with being wrong because we're just going to clear it up. So I'll start working this in 5, 4, 3, 2, and here we go. Right off the bat, I don't know what the angle is. We're trying to find that angle. I'm going to sketch a free body diagram to the best of my ability. So I'm always going to start with this incline, and it feels weird, but it does help. Here's X and Y. Those are my axes, and we'll just stick by convention. Gravity goes this way. So we are looking for this angle, and some angle here anyway. This is gravity pulling down. Force of gravity. As we go through this, it is often helpful to try to make sense of the problem and reword it in a way that hopefully will be, helpful in the end. So we're looking for when is this going to be, first off, relative to the vertical. So here's my angle theta. There it is. And I'm trying to figure out when is the parallel component half the perpendicular. So parallel to the surface is what this is referring to. If I were to draw my right triangle here using theta, this is the force that's parallel to the surface. And then it also asks me, when is this value, F parallel, half of the perpendicular? And I'll make that a little bit more bold. So by drawing this, we can start to make sense of what the problem's actually asking because it's kind of ugly. I would strongly recommend in situations like this, if you need to, draw what they're giving, ask questions if you don't understand the language, but if we can reword this question, it's going to be a little bit easier. This is really just asking, when is the parallel component, which I have labeled in red as F parallel, equal to half of the perpendicular? So cool. I want to know, when is this equal to 1/2 of the perpendicular? And I'll switch back to my green color. F perpendicular. That's all this is asking. Now, it's going to feel unnatural. I will talk out. Maybe it will, maybe it won't. Maybe this just feels completely natural and it's easy and I'm making it convoluted. I hope that's not the case, but it could be. Let's look at just this F parallel real quick. If I focus in on just this triangle, right here, this lovely guy. Okay, I know that I have an angle theta. And if I'm trying to find the parallel, that is the opposite side. And I'm going to use FG all the time because presumably we'll get a mass out of this at some point if we had to actually do the problem or do another problem like this. But here's what I'm thinking. Sine of this angle theta will give me the opposite, and I just need the hypotenuse. So I'm going to start with that. Sine of theta is equal to the opposite, which is my parallel component, over the opposite, or the hypotenuse, which in this case is just the overall force of gravity. What this allows me to do is by multiplying both sides by the force of gravity, I then know that, hey, the parallel component is equal to the force of gravity times the sine of whatever angle theta I'm dealing with. Okay. What I would recommend doing, and what I suggested to everybody else, is for this perpendicular, we're going to think of another trig function. So the perpendicular here, this green one, from this angle theta that's down here in the triangle, perpendicular force is adjacent, and I'm still going to deal with the hypotenuse. So what I think I could do is cosine of theta is equal to the adjacent on this triangle, which is the force perpendicular, over the hypotenuse once again, which is still the force of gravity. We can solve this for F perpendicular and then start to solve this equation. There's a little bit more math than we've covered in here, but I think you've seen enough trig in your day to work this out. If you get this answer, that's awesome, great. If you get close but you're not quite there, awesome, great. If you don't try it at all and you say, I don't know what to do, and you don't try anything, bad. Try something. Solve for F perpendicular. And then, according to this equation, we're just going to plug in. I'll even do the first part for you. Once we do this little scratch work, I know that I'm going to get the force of gravity times the sine of theta. That was the perpendicular, or the parallel force. I know that this is exactly equal to 1/2, and then whatever you solved for here. Your F perpendicular. We have this, and then your goal in this problem is solve for theta. That is your work this weekend. Solve for theta. I hope this video helps. It was a little bit more streamlined than the lesson in class, but we'll deal with any issues as they come. Good luck today on your game if you're watching this before. We will likely be watching it in physical science, but awesome. Feel better, play well if you're out traveling, and I'll see you guys on Monday with this problem complete. Cool. Later, guys.